So equation of motion is done. Conservation of work energy theorem is done. And now we are at conservation of mechanical energy. Excuse me. So what does conservation of mechanical energy theorem states? When only conservative forces like gravity act on a system. Now you might wonder what is conservative force. See, it's actually a very beautiful concept, something that I don't want to briefly explain. We will go through much in depth of the concept when we discuss about the solutions to questions based on work energy power. Okay, so for the time being, let's just focus on this one. When only conservative forces like gravity acts on a system. So your takeaway is gravity is a conservative force, and when only gravity is acting, you can make use of this concept, conservation of mechanical energy. The following is true: total mechanical energy stays constant. What is mechanical energy? Sum of kinetic energy and gravitational potential energy, or in simple terms, potential energy. Which means half mv squared plus mgh will be constant throughout the motion. What's interesting here is to understand that m into g into h height, this height is measured always relative to a ground, not to a ground level. It is measured relative to any level, to an arbitrary level. Now, which any height can be taken as reference, and you'll arrive at the same answer numerically if you follow the sign convention properly. So it is your choice to choose a reference for calculating height. Would make more sense while we discuss the question, the solution in detail. So if a ball is dropped from here, you can choose this to be the reference. You can choose the point of dropping A as a reference, or you can choose the ground B as the reference, or you can even choose a point C, somewhere like this, midway. Or you can even choose any point even more than that. Okay, and by all these methods, you'll arrive at the same solution. So for the ease of calculation, what I have done is I have taken the ground where the reversal of velocity has taken place as the reference height. So like we did in work energy theorem, we'll divide this problem into the complete motion into downward motion and upward motion. In that downward motion, we'll apply conservation of mechanical energy to find out the initial to final position and then find out the corresponding kinetic energy and potential energy, which was work done and displacement, force and displacement in work energy theorem. Okay. Likewise, in upward motion. So A is the initial position, B is the final position when the ball is falling downwards. It undergoes reversal of velocity. It starts moving up after the bounce. C is the initial position for the upward motion, and D is the final position for the upward motion. So far, good? Now, during the impact, when only conservative forces like gravity act, total, which is the kinetic energy, potential energy, is conserved. Net work done is zero because positive work by gravity on fall is cancelled by negative work on rise. Let us not spend much time on that. During contact with the floor, due to forces like friction, which is a non-conservative force, what does that imply? If the body is acted only by gravity, you can apply conservation of mechanical energy theorem. It holds true. But if it is acted upon by gravity and the force of friction, friction being a non-conservative force, conservation of mechanical energy cannot be applied. Why? Because some part of the mechanical energy will be converted to heat or sound or maybe light, as we see as sparks, right? So since that conservation is not taking place, well, actually, it's very simple. Since that conservation of energy is not taking place, therefore friction is a non-conservative force. just to make it as simple as possible. Having said that, it doesn't mean we will not go through in detail. We'll go through each and every force, which is conservative and non-conservative, and then we try to understand why are they named so. Okay. Now, coming up for the downward motion of the ball. Initial position is, wait, yeah. So initial position is A, ball is falling downwards to B, velocity is VA at A, kinetic energy is half mVA squared, and the corresponding potential energy, gravitational potential energy is m into g into HA. Now, why am I saying gravitational potential energy as if some other other forms of potential energy exist? Yes, it does. For instance, spring potential energy or elastic potential energy, to be more precise. Okay, so that's why emphasis on gravitational potential energy makes significant here. Okay, at the final position, which is at B, velocity is VB, kinetic energy is half mvb square, and the potential energy is mghp. And references this level where the ball is bouncing, where the ball is hitting the ground. Okay. Now let's apply the conservation mechanical energy of conservation of mechanical energy statement here. Initial kinetic energy is half mva squared. Initial potential energy is mgh into mgha. Final kinetic energy is half mvb squared. Final potential energy is mgh into hp. In this, velocity initial is equal to 0. Therefore, this term becomes 0 plus hb. HB overlaps with the reference height h equal to 0. Therefore, HB is also equal to 0, which means this term is also equal to 0. So this becomes plus 0, which gives us mg into 9.8, which is HA. Why HA is 9.8? Because the ball is dropped from a height. The ball is dropped from a height. H is equal to 9.8 meters. So what we get here is mg into 9.8 is equal to half mvb square. M by m is 1. And we have 2 into g 9.8 is vb square. Vb is 14 meter per second. Right? Now, again, what happens during the upward motion? Initial position is C, final position is D, corresponding velocities are Vc and Vd, corresponding kinetic energies are half mv so Vc square and half mvd square, and the corresponding heights are mghc and mght. Okay, and the reference here is h equal to 0, which is the ground, which means exactly hc should be equal to 0 here. And the ball is rebounding and it is rising to 5 meter. Therefore, HD should be equal to 5 meter here. Right? So, if we apply the conservation of mechanical energy statement here, initial kinetic energy half mvc square, initial potential energy mg into hc is equal to half mvd square plus mg into hd. What is hc? It is 0. What is vd square? vd is 0. Therefore, vd square is also 0. Why is it 0? Because the ball is momentarily at rest. And why is it momentarily at rest? As we discussed earlier, the, the ball, it falls like this, it bounces back, it stays up in the final position for it was dropped from 10 meters, it hits the floor, it bounces back and reaches the maximum height. At that height, it stays there for the moment and then comes back. At that moment, it is at rest, which gives us half mvc square is equal to m into g into hd. hd is 5, g is 10, m by m is 1. So we have vc square is equal to 2 into 10 into 5. Vc is 10, and the calculation remains the same. Again, bring up direction. Why? Velocity is a vector. Acceleration is a vector. Average acceleration is a vector. Bringing up velocity, taking downwards as negative, upwards as positive. V1 is equal to minus 14, V2 is equal to plus 10. Delta V is V2 minus V1, 10 minus 14, 24. Time is 0.2 seconds, which is 120 meter per second square as average acceleration. One problem, three different solutions, same answer. Three different concepts, same answer. Now you are more confident at the same problem. How? You are confident at the same problem, but you have strong concepts in three different chapters. Okay? Well, technically two different chapters. Motion in a straight line and work energy power. Okay, so that was the story with conservation of mechanical energy. Now let's take a break and maybe let's do some questions on, or maybe let's focus only on motion under gravity. Motion under gravity.